All right, everyone, let's jump in. So we're going to start moving forward with content today, and we're just going to take it one step further with our predicting products and answer a lot of the questions that we've already been asking, looking at how do we know? How do we know if a reaction happens or not? We saw in our lab that a double replacement reaction doesn't always happen. You don't always get a solid. Or we talked about how a single replacement reaction might not always happen. So what we need to look at today is how do we decide? How do we predict without looking at an actual experiment? How do we predict if these ionic reactions will happen or not? So we're going to look at double and single replacement separately because they followed separate rules. Okay, so to start, let's take a peek at our single replacements, right? So the main question here is, will the element be able to replace one of the ions in the compounds, right? If we notice, we see that, right here, we've got our cationic and our anionic single replacements where we have an element replacing an ion that is of the same type as the element, right? They would both make the same kind of ion, right? A metal replaces a cation, a non-metal replaces an anion. So the idea here is, we talked about in class, right? The replacing element, the one going in and kind of stealing the partner, has to be better in some way. We kind of joked about dancing in this regard, but it really is that incoming element has to somehow be better. And in this case, we mean more reactive. Okay, and there's a tool called the activity series that we're going to get to use to talk about this. Okay. Oh, sorry about that. That was not what I wanted to do. Then we've got our double replacements, right? And for those, we're looking at I'm sorry, what are we looking at? We're looking at the, let me just cover this up so it's not distracting. We have, we're wondering if it forms a solid or not, right? Like, will one of those products be a solid or not? Because if not, then no reaction happens. That's like you just mix the liquids together and it's still just a bunch of liquids, right? So we would have to have one of these become a solid. They both could. That'd be fine. It'd be an awkward reaction, but they could. But really, you're looking for one solid product. So you need to look at those new combinations of ions and then decide, will it be a solid or not? And for this, we get to use something called solubility rules. Okay? So, oh, gosh dang it, I keep doing that. Here we go. Let me get this out of the way again. So again, single replacement, double replacement, you're looking at either using the activity series to determine if it's a single replacement reaction, right? Which will the element replace it or not? Or you are using the solubility rules to determine if a solid product will form in a double replacement reaction. So let's jump in to the single replacement. So here's our activity series. I'm posting a resource with both this activity series list and the solubility rules. It's in your module. So that's up there. But the thing to think about with these single replacements and using the activity series or reactivity series, it means the same thing, is that, right, metals are going to react by giving away electrons. They become a positive ion. That's what they do. It makes them happier with their, stable octet and all that good stuff, right? So the metals that are better at giving away electrons are going to be generally more reactive. So you see those elements that are, on the far left of the periodic table, closer to the bottom of the periodic table, usually, not always, those are going to be your more reactive metals, better at becoming an ion. For the nonmetals, same thing, right? They react still to become an ion, but they do it by taking electrons and forming that negative ion, right? So those nonmetals, think of the halogens that are better at taking electrons, so like fluorine, right? Highest electronegativity, most strength in its nuclear charge and effective nuclear charge, it's going to be best at taking an electron and becoming an ion. So again, the element that gets to be, that is the better ion, gets to become the ion, the element that's more reactive, right? So let's look at some examples. I think it'll become really clear. If we look at lithium and sodium chloride, we would just have to compare lithium and sodium. So here is our lithium, here is our sodium. Lithium is above sodium on this activity series, meaning it is more reactive. So the lithium is more reactive, and therefore we will get a product, and we will get our sodium coming out as the metal, and then we will get a lithium chloride in solution because lithium is better at being an ion. Now, if we look at those same two elements again, but this time sodium is the element coming in, well, sodium is not more reactive than lithium, so sodium could not replace it, so we would have no reaction. Now, for the halogens, same exact principle applies, right? So if we have our fluorine and chlorine is what I'm comparing here. So here's our fluorine, here is our chlorine. Fluorine is above chlorine, it is more reactive, right? So we can see that in this case, we would have fluorine being able to replace chlorine. So here we would get our chlorine gas and our NaF. But then down here, chlorine, like we see, would not be able, and that should have a 2 there, I'm so sorry. Chlorine would not be able to replace the fluorine, therefore it would be no reaction, okay? So the element trying to replace an ion in a compound for a single replacement reaction must be more reactive than the element whose ion it is trying to replace, okay? All right, then we will move on and look at our solubility rules. So again, I'm going through this without a ton of breaks in between because I want to give you guys, you can pause it and record your notes and all of that, and go back through the kind of examples we've done, and then there's going to be other practice problems and questions that are going to come up as well where you can spend a little more time on it, okay? So digging into the solubility rules, same idea. These ones are a little clunky until you get used to it. So one thing you really want to note on these solubility rules is that when it means that it is soluble, I'm looking, you know, up here at the top of our solubility rules here, but when it says that a compound is soluble, that means that it will be aqueous in solution. If it's an exception, meaning it's not going to be soluble, that means that it's going to be a solid in solution. So flip to the other side, now we have a list of things that are insoluble, meaning they are solid, and then we have our exceptions that you can follow, and those ones would lead to something being aqueous. So let's definitely start there, and I am going to, sorry I didn't do this already, but I am going to go ahead and cover, oopsie, no, go away, sorry guys. I wanted this to be perfect for you, my bad. I just really want to get this out of our face. Okay, there we go. Let's just cover that up real quick. All right. So we use these solubility rules to determine if a compound is going to be aqueous or solid. So let's walk through how we do that. If we're going to look at sodium phosphate, it's just that first example, we need to either find the sodium ion or the phosphate ion up in the solubility rules. So I'm going to look for the cation first because why not? And usually I end up looking in this column first, just to see if it's there. And then you get used to the really common ones as well, like sodium, right? Here, I've just found sodium. Sodium is soluble. It's going to be aqueous. There are no exceptions. So I know for certain that this is aqueous. I don't even have to look at the phosphate because I know the sodium means it's going to be soluble, right? Or I mean, it's going to be, yeah, soluble, sorry. Right, so that's enough. You don't have to identify both ions because it's about the partnership. So if one of them says, yes, if there's a compound with this, it's going to be aqueous, then it is. So if we look at calcium chloride, I guess I'll do that one in red. Oh, here, I'll fix that too. Hang on, let me fix that. Oh, I'll make it so fancy. We'll make that one aqueous, right? For calcium chloride, so again, I'm going to look for calcium, I don't see group 2s, I don't really see calcium anywhere as I'm looking, except as an exception for hydroxide, so that doesn't help me. So I'm going to look for chlorine now. And I'm going to go, hey, halides, look at that right there. Halides are always going to be soluble or aqueous, except here there are some exceptions if it's with silver, lead, or mercury. That is not the case here, so this one will, in fact, be aqueous, okay? Then for our silver chloride, we just found chlorine, so that's awesome. And hey, look, there's silver, so this one is going to be a solid. Lead carbonate, so we can peek and see. I don't see lead. You're usually not going to see all the random obscure metals. But if you look, here you go, you see carbonate. Carbonates are almost always going to be insoluble or solid unless it's with a group 1 or ammonia, which it's not. It's with lead, so therefore this is going to be solid. Okay, so that's the process that you go through when you are trying to figure out, is a compound going to be soluble or not? So let me just erase this out and come down here, and let's work through this one example real quick to finish off the lesson. And for this, what I want us to do is I want us to be able to look at a, excuse me, a double replacement reaction, and I want you to, I want you, to be able to then also model what's going on using a new kind of small particle model that we haven't really worked with much. So, first of all, let's predict our products. So we'll come in and we'll see we have ammonium sulfate, or sulfide, and copper chloride. So if I just switch the ions, I'll have ammonia, or the ammonium ion with chlorine. Those are both single charges, so that'll just be NH4Cl. And then I will also have my sulfur with my copper. Copper in this one is a single plus charge because of the chlorine, so I know I need 2 of those. So that'll be Cu2S. So now I need to determine, are either of those going to be solid? And so I'm going to look at my solubility rules. The first one has ammonium ion, always aqueous, and chlorine, always aqueous. So this is obviously going to still be aqueous. The copper sulfide, here I can look and see that I do in fact have a message for sulfides, and as long as it's not with a group 1 or an ammonium ion, which it is not, then it is in fact going to be a solid. So we did our predicting, we did all of that. Now what I want us to do is work through a small particle model. So for beaker models, which is what this is, what I want you to show is what is actually going on in the beaker before and after the reaction, right? So in the beginning, this is right before the reaction. And over here, this is right after the reaction, right? So before the reaction, and here's where we do actually need to do some kind of coding. So I'll make a kind of rough key here. I'll show you some other ways to do this another time, and I will absolutely make that not a confusing color. So sulfide ion is going to be orange, ammonium ion is going to be purple, copper will be green, and chloride will be red. Okay, so before the reaction happens, oh, and we need to balance. Sorry, I forgot about that. Let's put a 2 there, and we'll put a 2 there, and then we're good. Okay, so to balance, we just need to show everything that we have. Before the reaction happens, everything is aqueous. So in water, which is really what we have here, right? This is all just a big, watery solution. So before the reaction starts, I know that I have 2 ammonium ions in solution. 1, 2. I also know that I have 1 sulfide ion in solution. I know that I have 2 copper ions in solution, and I know that I have 2 chloride ions in solution. And this is just from that balanced equation, right? And I'm putting them separate from each other because they are aqueous. They are dissolved. They are not connected. Okay, it's different than modeling a balanced equation like we've done with our single replacement reactions before. So then after the reaction, that's where we can model having a solid. So we know that the copper and the sulfur are coming together and forming a solid. So we have Cu2S, so our sulfur is orange. So I know that I've got my little orange sulfur, and I'm just drawing it bigger to show you a zoom here. I probably shouldn't have done that, but it doesn't need to be bigger. Copper was green, and there are 2 of them. So I'm just going to attach it so that it's obvious that they are attached, right? Just modeling, it doesn't have to be perfect. Let's see here. Now I still have my aqueous ammonium chloride, so I still have my 2 ammonium ions, and I still have my 2 chloride ions in solution, right? So what a beaker model does for us is it's able to really show us, hey, look, something is changing. It is definitely different, and it also really is great at illustrating if something doesn't happen, right? If you have a double replacement reaction that does not form a solid, and you look at the beaker model before and after, you will see both beakers are simply full of dissolved ions, and nothing, in fact, has happened. Okay, so I think that's where I'm going to call it for today. I want you guys to dig into this and go dig into the simulation, and that will really help you figure out through these, especially the double replacements with those beaker models, but actually it shows both. And then I'll be posting up some extra practice problems with worked solutions as well, just in a separate video. All right, bye-bye and good luck.